Good afternoon, students. I'm Dr. Abdul Hamid. Today we'll go through the elective paper B, that is material science. So in this material science, today we'll start with the first unit, that is mechanical properties. We are going to see what are the mechanical properties we have and how important in the material science is this. We'll see here. So if you see about these mechanical properties of the materials, uh, we have mainly different properties of material, we have stiffness, strength, uh, toughness, creep, impact, and its conditions. These are the main mechanical properties of the materials which we have. So we'll see what are those properties, and also we'll discuss the properties like elastic property as well as the plastic deformation. As we know that elastic property means when we apply some amount of force on that material, it is going to be what we call increases its length. Otherwise, we can say that when we apply some force on that material, it will increases its length. Now, afterwards, when we remove that force, it will regain its originality. That is what we call it as a elastic property. We call, and we'll see about this plastic deformation. That plastic deformation is nothing but, suppose if you apply certain amount of force on the material, beyond the limit if you apply, what will happen means that material will not regain its original position. That is what we will be calling it as a plastic deformation we are going to be called. Okay. And we have some mechanical properties of material which determines what we call how the applied forces will affect the size of that material, shape of that material, and how it changes its shape in movement. All these we'll see what are those. And you should know some fundamentals of what we call of the material. Otherwise, we should already might be studied what is Young's modulus. Young's modulus is very important in this studying mechanical properties of the material. We know that Young's modulus is nothing but that simply we can define that it is a ratio of stress and strain we have. And we should know about the rigidity modulus. Rigidity modulus is nothing but the shearing stress by shearing strain, and we have some relation between them. This what we call Young's modulus and rigidity modulus. That G is equal to Y by 2 into 1 plus VV is nothing but the Poisson's ratio. So similarly, we should know about the tensile strength as well as the tensile strength, and we should know about the compressive stress, the bending strength. All these we should know. Okay. And mainly, we should know about the stress and strain. Generally, stress, we can define it as a force per unit area. We can define. Okay. And coming to this, we'll see in detail about the mechanical properties. First, we'll see the first mechanical property of the material, which is a what we call a tensile strength. Here, we'll see what is tensile strength. So, first property which we are going to see is the tensile property. Tensile property, that is tensile strength. Actually, it is. So, what is tensile strength? All those we'll see now here. So, this tensile strength is the simplest of the mechanical test methods we have. which understand with the help of this tensile test, we can understand and we can evaluate the strength of the material. Okay, then with the help of this tensile strength, we can evaluate the strength of the materials or metal which we can use in like what we call it any structural design or in any engineering uh, importance what we have. So this tensile strength is it is a mechanical properties of metals and alloys are which are very useful in engineering importance and as well as the structural design. So therefore, it has to be follow some properties, important properties. Under these tensile strength, we have different properties are there. Like first one, we'll see the modulus of elasticity. Under this tensile strength, we should know about the modulus of elasticity of the material. Modulus of the elasticity of the material. So this test, if you will be considered as a first part of the tensile strength, we can consider. Uh, that means here in the main case, here it is. If you apply some uh, force on any material, that is any metal, whichever you are going to be taken, where the metal is deformed elastically. So elastically, how it is deformed, we'll be seeing here. Otherwise, what is that is if you apply some load onto the material, okay, if you apply some load onto the material, then afterwards, if you release this load from the material, then what will happen means the material will come back to its original condition. Okay, material will come back to its original condition. And if you see uh, any metals, if you see, so these metals are having a maximum elastic deformation along, usually less than 0.5 percentage. Okay, 0.5 percentage. So if you apply more than this 0.5%, then what will happen means the metal whichever we are using in this will not come back into the original position. That means it cannot come back into the uh, original position of the metal which we have before applying the load. That means the load which we are going to be apply onto the material is having certain limit. That limit is up to 0.5% only. Okay, so these metals and alloys show some relationship between the stress and strain in the elastic region. That means whatever may be the stress you are applying and stress and strain whichever you are applying, that should be applied within the elastic region. If you apply this stressor and the strain beyond this elastic region, if you apply, then what will happen means that metal will not come back its original position, but whereas it will deforms. That means its original what we call a position will be original shape will be not getting back. So that is what happens if you apply the stress and strain beyond the limit that we will be calling it as the elastic region we are going to be call. So we have some diagram like a stress and strain diagram is there. So I'll show that stress and strain diagram here. Uh, so here we have that 1 minute. One minute. To the stress and strain diagram. So I'll show you the stress and strain diagram here. Uh, right. So this is what we have. So this one, whichever we have, like this is a curve between the stress and strain curve. So we are having stress on strain on the x-axis and the load on the y-axis. So if you see here, within this range, whichever we have, this part, whichever we have, so there what will happen means this one, this region, whichever we have, right? So this region, whatever we have, this one, right? So within the region, if you apply, 1 minute, okay. So within this region only, when we apply, what will happen means it will regain its original position. Otherwise, it will not come back to the original position. We'll be calling that as a the stress and strain curve which we have here. Okay. So now we have like a, suppose if you take any what we call we have like a different materials which we are made up of, like aluminum, copper, steel, or tungsten. So if you see the modulus of elasticity for different cases, like if you compare like aluminum, copper, steel, tungsten, so highest value is tungsten. We have like a 400 what we call a GPA are there. So that is gigapascals we are going to be called. Uh, this is what the value of the modulus of elasticity, and also we have like a shear strain is there. So this shear strain is also having a highest value for tungsten. That means the modulus of elasticity, whichever we have, that is more in the case of the tungsten. Means if you apply more amount of force on that, also what will happen means within the elastic limits only, when you apply, it is going to be increases its length. That is nothing but when you apply this force on that one, that is stress and strain, the what we call the lengthwise, if you see, the tungsten is having higher value modulus of elasticity. Okay, and whereas aluminum, if you take, it is having less modulus of elasticity and as well as the shearing strain here. Okay, so why that is the Young's modulus, whichever we have, is known as the modulus of elasticity, Young's modulus. So the modulus of elasticity here, it is related to the bonding strength between the atoms and metals we have. So that is a bonding strength of the atoms of a metal or alloys. That is nothing but inside metal, whatever may be the atoms, the bonding between them atoms is going to be strong in the case of the tungsten, whereas in the case of the aluminum, it is going to be have less. So this is about the what we call the first property of the tensile strength, that is modulus of elasticity. And then after we'll move to another property which we have is yielding strength. Okay, next we have is yielding strength. So this is also one of the most important property of this important property of the mechanical properties, yielding strength. That is nothing but if you take any structural design, if you take this yielding strength value, whichever we have, the value of the strength of the material, which is material which may be like a metal or alloy, whatever it is going to be have, it shows the significant plastic deformation. Okay, it shows the significant plastic deformation. That is what we have. We call it as a yielding strength. We are going to be called. Then after we have like another one which is a tensile strength. Okay, tensile strength. So this tensile strength is nothing but another important property of this we have, which is a tensile strength we'll call. Okay, so tensile strength, this is also one of the important property which we have. So this tensile strength is nothing but the maximum strength reached in the stress. Okay, stress and strain curve. The maximum strength which is reached in the stress and strain curve is known as what we call the tensile strength we are going to be called here. Okay, maximum strength reached in the stress and strain curve is called as a tensile strength we are going to become. Suppose in the case of any material, that means any metal which we use uh, in making any material, so stress decreases with further by increasing the strain. Okay. If a specimen develops necking, that is nothing but the cross-sectional area, the engineering stress decreases with further increasing the strain. Okay, that is what we'll call this. So the tensile strength is nothing but mainly it is going to be measured the maximum strength reached in the stress and strain curve is called it as what tensile strength we are going to be called. And similarly, we have another definition in this one. Uh, Another definition which we have here. Another one is we call it as a percent elongation. We'll call, okay, percent elongation. So percent elongation is nothing but um, so when we apply some amount of force, that is nothing but how much amount of elongation that takes place in the particular specimen. Okay, during this process, we'll be calling it as what we call during the process, which gives the value of ductility. So generally, this percentage of elongation we can define as it is the difference between the final length to the initial length divided by initial length. So we can write this percentage of elongation is final length minus original length, or we'll be calling it as the initial length. So initial length is nothing but the length which is there when we have not applied any what we call a force. Okay, when we have not applied any stress on that one. Into 100 is going to be percentage length. So final length is nothing but after applying certain amount of force. Okay. After applying certain amount of force, it is going to be get final strength. Then final strength minus initial strength by initial length into 100 is known as what percentage of elongation you are going to be called. So generally this percentage of elongation we can represent like L minus L naught by L naught into 100 we have. So this L naught is nothing but the original length and L is nothing but the length after applying certain amount of force on that one. Okay, so that is what we have, the percentage of elongation. Right. And similarly, this we can measure in terms of what we call percentage reduction in area also. This is a percentage of elongation and lengthwise we can measure. And similarly, we have like a, percent reduction in area. Okay, percent reduction in area we can call. So this percent reduction in area is nothing but again we can measure in terms of area. So this is going to be what we call final area minus initial area by initial area by uh, the difference between the initial area and final area. Here we have like a what we call initial area minus final area by initial area. Sorry, final area minus initial area, right, divided by initial area into 100. So we can write it as a final area as AF minus AI by AI into 100 we can write here. Okay. So the percentage reduction in area can be calculated by this formula, that is AI minus AF, AF minus AI by AI. So the percentage of reduction area may be generally decreases if defects such as what we call some porosity inside of the material or some inclusions are there inside of the material. So this percentage reduction will be decreases. So this is also one of the property which we have. And then we have like we should know about creep. 1 minute. Right. So next we'll to right. So what is creep we'll see here? This is also one of the mechanical properties. Creep is nothing but when we take any metal or alloy, when we take. So when this metal or alloy, if it is undergoing some constant load continuously or some stress continuously, then it may happens. That means it may undergo some deformation over a period of time. So what is that is in the creep is nothing but when you take any metal or alloy, if this metal or alloy which is undergoing a constant load, that is nothing but we are maintaining some load on that one continuously for a period of time, or some stress on that particular material for a period of time, then what will happen means this material or metal, whichever we have been used, so this undergoes some deformation over a period of time. So after a period of time, some deformation is going to be takes place in that material. Okay, deformation is going to be takes place in that material. So this, whichever we have, that is nothing but with respect to time, if it is undergoing some deformation, so this kind of time-dependent strain, we'll be calling it as what creep we are going to be called here. Okay, and this creep is very important in the case of the metals or alloys because of in some applications like in technological application or some engineering structural applications, it will plays very important role. Why? Because suppose if you take any one example, if you take if you are having any turbine blades of gas turbine, so if the material having which is having very low creep value, otherwise very low creep rate, then only what will happen means these turbine blades or gas turbines, turbine blades of gas turbines will be effectively will be present for a longer period of time. Suppose if the creep rate is more, if you are having, then automatically what will happen means there will be the durability of those turbine blades will be less period you are going to be have. So we have to be choose the material which is having the creep rate is very less, which we can choose for any applications of like any engineering applications where we are going to be have. Like as I told that example, if you take any turbine blade of gas turbine, then if creep rate is more, if you are having, automatically the duration or lifetime of those gas turbine blades will be less. So if creep rate is less, then automatically these turbine blades of gas turbine will be having a lifetime more you are going to be have. So that is what one example we have. And like this, depending, we have some like this, we have some applications in the engineering. So we have to choose the material or alloy, whichever it is having the creep rate less. So the creep rate, it will represents that how the metal or alloy is deforming over a period of time, it will tells. Okay. Similarly, we have another important property in this, which is impact strength. Impact strength. Right. So this impact strength or impact the toughness, we can say that impact strength or toughness, we can say that. So mainly it is a measure of the amount of energy where a material can absorb before attaining the fracture. Okay, impact strength is nothing but it is a measure of the amount of energy where a material can absorb before it comes to the fracture. Okay, So, and moreover, this impact strength explains the ability of a material to withstand without fracture. Okay, so we can say that what is impact strength is nothing but it uh, explains the ability of a material to withstand without a fracture. That is also known as impact strength or toughness of the material. We can say that. Okay. So to measure this impact strength or toughness, we have like some machinery out there, which we will be calling it as a impact test apparatus. We are going to be called, and this is also known as some machine name is there. So which we will be calling it as a CHRP impact testing operator. We are going to be called. Okay, CHRP impact testing apparatus. We are going to be called, and if you see this. Uh, this what we call impact strength, it also dependent upon what we call the temperature of the means the temperature with which the material which is holding. Okay, so that is nothing but generally these materials in applications where we are using, so they are going to be used at higher temperatures. So this higher temperature also will impact the what we call strength of that machine, or toughness of that machine is going to be impact. So this what we call temperature also plays very important role. So generally what will happen means as the temperature is increasing, automatically what will happen means the toughness value is going to be changes with temperature also. Okay, that is nothing but the amount of energy which is going to be absorbed by the material is also going to be changes when the temperature value is going to be changes. So these are the important properties which we have to see when we are choosing any metal or alloy which will be utilized in engineering applications, or in the materials which we using for any application. Okay, so these we'll be calling it as what mechanical properties of this what we call material. And moreover, we have to see that the material which we are using for any applications, these has to be tested for different that means it undergoes different testings also. So the materials are tested by engineers to ensure the what we call the chemical composition. Okay, means the any material whichever we have been taken, so that metal or alloy is undergoing to be what we call in test of chemical composition, and as well as the whether the metal whichever we have been taken for in a particular application, whether it suits for that one or not. That is also undergoes. That is the suitability of material for particular application. Suitability of material for particular application also we have to check. Particular application also we have to check. And also right. So then uh, the materials, they the whichever we have been chosen, they'll check the ductility of that material, as well as the toughness, as well as the malleability, etc. Okay, they'll check the fundamental properties like what we call ductility of that material, they'll check, and as well as the malleability, and as well as the toughness. Okay, all these properties they'll check whenever they are going to be choose certain material for any engineering application. Okay, and as well as they'll check the stress values so that one can design uh, for a particular. application for they'll mention the specific of this stress value. Okay, the stress values also they'll check, and as well as uh, they'll determine any what we call defects like surface defects they have. Okay, so they'll check for any surface defect whether it is having or not. They'll check, and as well as this what we call there'll be what we call they'll determine some mechanical properties which are very important. That is nothing but they'll check this tensile test they'll do, and as well as the impact test they'll do, and as well as the what we call a hardness test. Okay, hardness test they'll do, fatigue test. Okay, fatigue test they'll do, and as well as the creep test they'll do, and as well as the torsion. Okay, so like this they'll be uh, all these tests will be done when they'll choose for any engineering application or any structural application. They'll choose all this. Okay, and these mechanical tests, whichever we have, they have further divided into two categories. One is they'll be calling it as what destructive test. Okay, they'll be calling it as a destructive test. They are going to be called another type, another category of this test, mechanical test, which we have is a non-destructive test. Okay, another one is a non-destructive test. These are the two categories which we have. So in the case of the destructive test, if you take, so in this destructive test, the specimen is destroyed and cannot be reused. Okay, the specimen is destroyed and this cannot be reused. So the tests are conducted on similar specimens under the same conditions. So generally the test which we use here in this tensile test, hardness test, as well as the impact test and creep test. So these tests will be conducted in the case of the destructive test here. Okay, in this process, the specimen is destroyed and cannot be reused. So the tests are conducted on similar specimen under the same conditions like tensile stress, hardness test, and the creep test. All these you are going to be conducted. And in the case of the non-destructive test, another category of this what we call mechanical test which we'll perform. So the specimens is not destroyed. That means the specimen whichever we are taken will not be destroyed. The specimen can be used after the test. Okay, the specimen can be used after the test. Under this non-destructive test, it undergoes so many what we call test like ultrasonic test. This undergoes, as well as the magnetic dust method, penetrating liquid method is there. So like this it is going to be uh, get here. So in the non-destructive test, mainly the specimen is not destroyed. The specimen can be used after the test. That is what happens. Okay, so some mainly uh, what we call important destructive test in detail if you see under the destructive test. Okay, under this destructive test, if you see, we'll be, as I told, that we are going to be conduct what we call a tensile test. We are going to be conduct. So tensile test, what it is going to be do is means under this uh, we'll understand. That means by doing this tensile test on a material, mainly the properties like what we call a elastic limit of that material, yield point or yield strength, breaking strength, percentage of elongation, modulus of elasticity, and so on can be known if you perform any tensile test. Okay, so this is one type of test which will perform on the material. In this tensile test, again, we'll be having like what we call we'll be having different types of samples. We have a round sample or a rectangle sample like that. We'll be having so many what we call different type of tests will be there. So generally, elastic limit will apply here in this case of this test. So that tensile test. So elastic limit is nothing but within the limit elastic limits, we'll apply the load to the original area of the sample. Okay, that is what we have. And another type of test which we'll perform under this destructive test is we'll perform what we call yield strength or stress. Okay, we'll perform yield strength or stress we are going to be performed here. So this yield strength is nothing but load maximum. That means load yield point by original area of the sample. Okay, this is what we call it as a yield strength. We are going to be called, and um, in this we have ultimate tensile stress will be there. That is nothing but the maximum load, ultimate load by the original area of specimen we have. We can calculate the percentage of elongation in length we can calculate, and as well as the percentage of reduction in area already we have discussed. We can calculate the Young's modulus, that is the stress by strain, that is nothing but stress at any point within the elastic region divided by the strain. We'll be calling it as Young's modulus. And similarly, we can perform the breaking stress, that is the breaking load by the original load we'll call. And this is under yield strength or stress we have. And one more we'll perform under this is a hardness test. Okay, hardness test. So under this hardness test, what we'll do is we'll measure hardness is measure of resistance of the surface of material before deformation. Okay, before deformation. So in this, in order to perform this hardness test, we will be having different types of tests are there, like a Brinell hardness test is there, Vickers hardness test is there, Rockwell hardness test, rebound hardness test, and scratch test. All these are different types of hardness tests. They are having what we call a different method to know the hardness of that material. So under this hardness test, we can perform the hardness test in different ways, like a Brinell hardness test, Vickers hardness test, Rockwell. Suppose if you take this Brinell's hardness test, this method is used to determine the hardness and quality of the material. Okay, the method is used to determine the hardness and quality of the material we have. And similarly, if you go for another type of test which we have is a Vickers hardness test. So this Vickers hardness test, if you take this method is also similar to this what we call a previous method which we have, that is Brinell's hardness test. So similar to that Brinell's hardness test only, but what will happen means with the help of this Vickers hardness test, the flattening of the steel ball is eliminated. Okay, the flattening of the steel ball is eliminated. So in the Vickers hardness test, we have some formula to measure the hardness of the material. That is a load applied in kilograms by the area of indentation. That is nothing but kilograms per millimeter square units we have. Okay. So these are the some different tests which we have. Okay. Next, we'll move to the models of fractures. So under the models of the fracture, we'll have a ductile fracture and as well as a brittle fracture. So next, we'll move to the models of fractures. . So fracture is nothing but a fracture which we can define as the separation of a specimen into two or more parts by an applied stress. That means when we apply some stress on the material, so it is going to be separated into two or more parts. Then we'll be calling it as a fracture. Okay. So these fractures, it is classified into two categories, namely, we have like a brittle fracture and as well as the ductile fracture. Okay, so one is brittle and another one is we have ductile. Okay, so these are the two categories of the fractures we have. So generally, if you take this ductile fracture, it occurs when account of plastic deformation, whereas a brittle occurs for non-plastic deformation. Okay, so if you take this ductile fracture, so under the ductile fracture, as I told that it occurs due to the plastic deformation and propagation of crack is slow in the case of the ductile, whereas brittle fracture, it is a non-plastic deformation. So in the case of the brittle fracture, we can say that example is glass. That means if you apply the force into the glass, it is going to be break down completely. Okay. Whereas in the case of the ductile fracture, what will happen means the crack which is happening is going to be slow. That is in the case of the plastic deformation. So plastic deformation, which is going to occur very slow, whereas in the case of the non-plastic deformation, this is going to be very rapid. That is, it is going to be like into two or three parts. It is going to be very early. It is not a slow process, brittle fracture. And under the ductile fracture, we can say that the surface is very dull. That means the smooth surface is not, that means the polished surface will not be there. The shining under the ductile fracture is very less, you are going to be have. Whereas in the case of the brittle fracture, if you take the shining will be more, fractured surface is shining and crystalline and appearance will be there. Okay. So if you take the ductile fracture, prior to the fracture, that means before the fracture is going to happen, the percentage of elongation is more, around 30% we have in the case of the ductile fracture. Whereas in the case of the brittle fracture, if you take the in the case of the brittle fracture, before the fracture, the percentage of elongation is around only 0.5%. That means if you compare the brittle and ductile fracture is having more elongation before the fracture. That means it can withhold some amount of stress on that one. Whereas brittle fracture, it will withhold only very little bit. Only it is having elongation process is 0.5 percentage only. Okay. In the case of the this what we call ductile fracture, the cross-sectional area is reduced, whereas in the case of this brittle fracture, no change in the cross-sectional area will be there. Okay, so these are some what we call ductile fracture as well as the brittle fracture we have. Okay, some fractures which we have. When we studied in detail about this ductile fracture, as I told that uh, it is a sorry brittle fracture. If you take this brittle fracture is associated with the minimum number of plastic deformation. If you take some features of this what we call brittle fracture, so the crack which is going to be takes place, it is very small. Okay, if a small crack will be there in a metal which grows and movement of crack is involved in less plastic deformation. That is the main uh, characteristic or property of this brittle fracture which we have. Okay. Uh, and if you take the surface of metal has higher energy than the interior planes. Okay, surface of this metal is having the higher energy than the interior plane. Moreover, at the surface, the atoms do not have as many as neighbors in interior side, and therefore forms bond. Okay, therefore they form a few bonds. The interior atomic bonds can easily be destroyed by means of normal stress. Since brittle fracture does not produce plastic deformation, therefore it requires less energy than a ductile fracture. So these are the some properties we have. Then we have another one, that is ductile fracture. So if you see this ductile fracture, so this fracture occurs after extensive plastic deformation and during the propagation of the crack. The main important steps which are involved in the ductile formation is the formation of what we call minute cavities in from neck region. That means this type of dislocation movement takes longest time in the fracture process. Okay, and they form like what we call at the central of the material cavities. That means the cavities which are they are going to be have, they will be at the center of the material you are going to be have. And so suppose if you want to prevent the fracture failures, so we have some methods to adapt to prevent the fracture failures. So what you have to do is, in order to reduce the tensile stress, okay, in order to reduce the tensile stress and crack propagation, one should introduce what we call some compressive stress we have to introduce. So this can be done by simply heating the material. Okay, this can be done by simply heating the material. So examples are like glass materials which are used in windshield automobiles. And by polishing the surface, one can remove the cracks on the surface. Okay, and avoid sharp corners to eliminate the stress concentration. This can be done at the design stage itself. So we have to avoid impurities at the base metal because they may introduce some brittle phases. Okay, we have to avoid the impurities. And one more thing is the stress applied direction should be parallel to the elongation. Okay, so and another one is by proper distribution of atoms at grain boundaries, one can avoid the brittle phase at grain boundaries. And moreover, fine grained materials offers good protection against the brittle fracture. Right. Fine grained materials offers good protection against the brittle fracture. And by using some composites, okay, composite materials, one can protect against the tensile loads. So these are the methods to adapt to prevent the fracture failures. Okay, some we have. And if you see the factors which affect the mechanical properties, this is very important. The factors uh, which affect the mechanical properties. Mechanical properties. So far, we have seen some mechanical properties which are important. So here we'll see the factors which are affecting the mechanical properties. The first property which is affecting the mechanical properties, the grain size. Okay. So first one is the grain size. Sorry, grain size. Okay. This is one of the important property of the material. Uh, Suppose if you take the fine grained metals have a higher strength and lower ductility. If you take a fine grained metals, if you take, therefore fine grain is very important and it is specified for any specific applications which have the higher hardness. Okay, which has the higher hardness. So effect of grain size and ductility and tensile strength is going to be there. So you have to we choose the fine grained metals we have to choose. So it does not affect any mechanical property. And also we have another property which is affecting on the mechanical properties of the mechanical properties of any metal which we have chosen, that is temperature effect. Okay, so temperature it will affect more. Okay, so this temperature will affect the what we call elastic limit as well as the Young's modulus and other properties also it is going to be affect. Suppose if you raise the temperature, okay, if you raise the temperature, because we have some machines which are going to be maintained at higher temperature in the engineering applications. So when we raise the temperature, what will happen means the yield stress, uh, toughness and tensile strength will decreases. Okay, the tensile strength will be decreases. Therefore, Young's modulus also decreases with increase in temperature. So we have to be choose the material in the application of any machine which is used in engineering applications. Like means the material which we are chosen to make that machine should be withhold higher temperature, because the higher temperature will decreases the toughness, tensile strength, and as well as the yield stress. All these values decreases at the same time. The Young's modulus decreases. So if all these are decreasing, automatically what will happen means it will affect the mechanical properties. So we have to be choose a material or some alloys which withstand higher temperatures. Okay, that is one main effect of the temperature will be there. And at higher temperatures, so generally around more than 450 degrees centigrade if you are having, so it also affects the creep. It also affects the creep. That means creep occurs. As we studied the creep, creep is nothing but as the time is goes on, the deformation in the metal is going to be takes place. So at higher temperature, creep occurs. So creep increases with time and reduces the toughness of that material. So we have to be choose that the creep value should be less at higher temperature. So we have to choose a material which is having the creep value is less. That means the deformation of that metal along with the time with certain load it has to be taken. So we have to choose creep value should be less. When we raise the temperature, that means at higher temperature, the fracture stress and stiffness of metals may be decreases. So that is also some factors which affects the mechanical properties. And if you take several metals and large number of alloys, which exhibits the phenomenon of superconductivity nearly at absolute temperature. Okay, that is also one factor which will be there affecting the mechanical property. Okay, and another property which will affect the what we call a mechanical property is exposure to atmosphere. Okay, exposure to atmosphere. Right. So when the metals will exposing, when metals, some metals exposing to the atmosphere, what will happen means they will get oxidized. So if these metals will get oxidized, due to this oxidation process, a thin film of oxide layer is formed on the surface. Okay, a thin film of oxide layer is going to be formed on the surface. So the presence of this what we call a chloride um, in marine atmosphere, that means where the sea is present, the presence of chloride will be there. So it increases the conductivity of liquid layer which is in contact with the metal surface. Okay, so that is also there. So when we go to the marine atmosphere, the presence of chloride increases. So due to that, the conductivity of the liquid layer which is in contact with the metal surface. Okay, so therefore the resistivity of the metal decreases in the presence of this air moisture. Okay, some like hydrogen sulfide or sulfur dioxide and some what we call other corrosive atmosphere conditions is going to be takes place. And within this humidity conditions, okay, within these humidity conditions, the corrosive action will increases, which will affect the mechanical properties and as well as the durability of that material is going to be decreases. Okay, the main thing is the corrosive atmosphere conditions. The durability of that material is going to be decreases. That will have the what we call atmosphere exposure will be affect the mechanical properties. And one more property, if you take, which will affect the mechanical properties, is another one we have is a heat treatment. Heat treatment. Okay, heat treatment. So this heat treatment will improve the mechanical properties like tensile strength, hardness, toughness, and as well as this what we call wear resistance. So in order to improve the following properties, like means if you want to improve some properties, we have to take this heat treatment is generally adopted for the material. So uh, if you do the heat treatment, the mechanicability increases and as well as the resistance to corrosion increases, as well as the chemical, electrical, magnetic and thermal properties will show improvement, and the mechanical properties like ductility, hardness, tensile strength or internal stress, and modification of structure and grain size will happen. So with the help of this heat treatment, we have some advantages than the disadvantage. If you perform this heat treatment to the material which we are using, so then um, we can get like a mechanicability, resistance to corrosion will increases, chemical, electrical and magnetic and thermal properties will improve. Okay, so if you want to improve all these properties, what we have to do is we have to perform the heat treatment. And one more property which will affect this mechanical property is that is carbon content. Carbon content. So carbon steels are widely used in engineering materials. Okay, carbon steels are we are using in engineering materials. So carbon steel is an alloy of carbon and steel, in which it is containing the manganese 1 percentage, silicon 0.5 percentage. We have sulfur 0.04 percentage and phosphorus 0.05%. Okay, so it should be remembered that sulfur and phosphorus material should be minimum while preparing, that you have to maintain. Carbon and manganese plays a significant role in mechanical properties. Okay, so if you use these some properties uh, when we use this carbon steel, when we use um, because of some properties like they are very cheap, means comparatively other materials. So properties can improve with further heating, and as well as the what we call easily we can shape, and in different sizes we can make it. It can be widely uh, it can be used, what we call it can consume less energy during the production. And one more thing is we can recycle it. Okay, and the welding process is easily in this one. So these are the some properties which are affecting. So if you see, we have to be choose a metal which can be used depending upon their applications where we are using. So whether we are using in the heat environment, or whether you are using in the like in the what we call humidity conditions where the marine is present. Okay. And similarly, we'll see the property